So, together with my co-authors, I share the passion of Paul Roberts to try and understand this very interesting limit called magnetostrophy, and he's done a good job of explaining what it's about. Of course, it never hurts to hear it for a second time, so you'll see an awful lot of commonality in the talk. So the conventional dynamo approach, which Paul talked about, was that you contain all the forces, you're limited by numerical constraints. The great thing is, from the last 20 years, that we've had success. It's been a great success, but they are perhaps a very specific class of dynamos, in particular that the viscosity is something like a billion times higher than it should be in general. So, as Paul said, magnetostrophic dynamos, in common with Paul and his collaborator C.C. Wu, we've worked on axisymmetric mean field dynamos with zero viscosity and no inertia. And I'm not really going to dwell too much on the results because the applicability of these axisymmetric mean field dynamos to the Earth is somewhat dubious and limited, but nevertheless they provide a very good test bed for the development, as Paul said, of these kinds of the techniques that we need to be able to approach this rather challenging limit. So let's just start with a little bit of discussion about physical constraints and approximations. And let's start with fluid flow with no sound waves. So, for example, if I want to model the circulation in the oceans, probably I don't want to have to deal with the singing and the speech of whales and porpoises. So I probably assume that the oceans are incompressible. And so I have a constraint such as the divergence of U is zero at every point. And that's of course easily implemented in numerical codes. We have mathematical theorems that tell us how to do that. Now, as Paul said, the inviscid inertialess problem is a little bit more problematic because we have a constraint at every cylindrical radius S, which is that this thing, which I call T, you'll see this throughout the talk. T depends on the magnetic field B, and T must vanish at each radius S. And the consequence of this nice approximation is that there are no inertial waves, no alpha-fin waves. Many people think that the dynamo probably doesn't depend on inertial waves to operate. Not everyone, but many people wouldn't think that it's too important on very long time scales. And what is this thing T? This T is the Lorentz torque on a cylinder, and there are an infinite number of cylinders within the core, so we've got a very awkward thing to have to implement in our models, but I'll show you how we seek to do that, as Paul has already shown you. So the revived approach, which Paul mentioned, is from J.B. Taylor. This is his paper. It's nice because it's got an equation in the abstract. You don't get that too much these days. And this is the celebrated Taylor constraint that we're going to have to deal with. So let's just briefly look at the equations. The Navier-Stokes equation and the induction equation are here. They've been non-dimensionalized. And as Paul said, we've got two very tiny parameters in the core. We've got the Ekman number here, which I say is something like 10 to the minus 15, and the Rossby number, which is something like 10 to the minus 9. It's the ratio of the rotation timescale to the magnetic decay timescale. So we'd like to actually put those to zero, and that's what leads to the nice magnetostrophic balance. And as Paul said, you can always just solve for U if everything else on the right-hand side is given, and indeed you need a Navier-Stokes solver. And if you want to learn about how we do that, there's a paper by Livermore et al. On Wednesday that you can go and look at. So in principle, this is a fairly straightforward thing to do. We work again in a whole sphere. There's no inner core in these models. Inner cores are way too advanced for where we are at the moment. And this is just to tell you where all this stuff comes from. So here's the equation of the force balance between Coriolis, pressure, Lorentz, and buoyancy. And what Taylor said was, when you integrate this thing over any cylinder coaxial with the rotation axis, you find this thing which I told you I would call T throughout. You find this thing must vanish. The Lorentz torque must vanish. J is the current density, B is the magnetic field. And it applies on every cylinder And then Taylor showed some very nice theorems about uniqueness and necessary and sufficiency of this condition. And there's a degree of freedom in the to allow this Taylor state to be achieved, and this degree of freedom is the geostrophic flow, which is called UG of S. So that's the underlying maths. Now, the difficulty, as Paul already mentioned, is that you have to really deal with two sorts of coordinate systems. A cylindrical coordinate system, which is needed for integration over these cylinders, and you need a spherical coordinate system for the mechanical boundary conditions and the insulating boundary condition on the magnetic field, and that's historically caused some problems. So the way we've got around this is to work entirely in polynomial subspaces. And we consider, in this methodology, we consider that problem now to be solved. We use the spectral expansion in all three directions. We're working in a whole sphere here. The boundary conditions are exactly satisfied. In fact, we use a Galerkin technique for that. And the basis is spectrally convergent for smooth solutions. And the key thing is that all the integrals can be done exactly, in particular these integrals over cylinders that we need. And the numerical method that we use is that we minimize a measure of this, the deviation of this Taylor constraint on every cylinder S. You can see that if I square that and integrate over all S, the answer must be 0 if you are managing to satisfy the constraint. W is a weight function, which is actually chosen to be a sort of a Chebyshev weight function. So the key things is that in principle the Taylor integrals are satisfied to machine precision. They can be satisfied exactly analytically, but in a computer program they're satisfied to machine precision. We can generalize this very easily to 3D. There's a difference between how we approach this and how Taylor suggested. So there's no differential equation to solve for the geostrophic flow. And if you want, thinking ahead, if people object to the fact that there's no viscosity here, we can actually introduce viscosity in a sort of asymptotic way in a subsequent generalization, but I think that's much further down the road. And the key thing that we do is to choose the geostrophic flow so that the field is in an exact Taylor state after we take a time step. So that's the key thing. That's what you always want to do. And this is a sort of classic problem in optimal control that was popularized in Lyon's book in the 70s, but originates even earlier with the Russian school. So that's the key thing. Our solutions are in a Taylor state after we take the time step. And here's a little example. This is a 2D mean field dynamo. These are the energy norms for the poloidal and the toroidal magnetic field. So you're stepping forward in time here. And the only thing that's of importance really here is this is the measure of adherence to Taylor's constraint. And you'll see that this number, 10 to minus 15, is something of the order of machine precision. So we can take, here we've taken 10,000 time steps with Taylor's constraint obeyed to something like 10 to the minus 15. So that all seems to be working quite nicely. Now I'll give you a little example of how this might apply. So we all know the classic problem of magnetic decay in a solid. In a solid, magnetic fields would decay if we have no energy source, and they'll decay according to this equation, and that's all you have to solve. And in a whole sphere, we know the analytic results. In a liquid, we have to satisfy this equation, and we also would need to then satisfy Taylor's constraint at every time. And here's an inviscid fluid sphere with free decay. The poloidal magnetic field is decaying. The toroidal magnetic field, you induce a toroidal magnetic field because of the flow. You induce some energy in a geostrophic flow. And here's the adherence to Taylor's constraint again, starting at about 10 to minus 16 and dropping. And in fact, the poloidal magnetic energy is not much altered from the solid analytic solution, which is minus pi squared. So anyway, that's just a sort of canonical problem. Oh, I went forward and Now, what if the Taylor constraint is not obeyed at all times? Well, we're going to get small oscillations, torsional oscillations, and in the words of Boyd, these define the sort of the fast manifold, and we think they're largely irrelevant for long-term behavior. They're not in Taylor's prescription. So anyone who knows this book, I really recommend it. Boyd, this is an example of the sort of what he calls the fast and slow manifold. And really, for dynamo action, we're only interested in the slow manifold. So I'll show you an example that we've computed of the fast and slow manifold, and it's an alpha effect dynamo. Again, we've got this alpha effect here. And the slow manifold would be exactly described by Taylor, whereas you can compare it if you wish. You can put the inertia back in with a Rossby number, and then you're going to get both the fast and the slow manifold. So I'll just show you this movie just before we finish. And we've got the poloidal and toroidal magnetic energies here, and on the right we've got the geostrophic cylindrical flow shown. And if we step through in time, what you'll see is that we've got some we've got some torsional oscillations that are developing in the geostrophic flow. So the flow is going like back and forth on cylinders. Now you see that the amplitude of this is about 30 at its peak and about 0 at its minimum. And if we were to average this over many cycles, you can see that we're going to get essentially something that's about 15 going, well, you're going to get a shape something like this. So this is the average over many torsional oscillations, and at the bottom here, this is what we compute when we actually impose Taylor's constraint. And what you'll find is that the two things essentially agree. If you impose Taylor's constraint, you get the background solution, or you get the background geostrophic flow, which you would have got if you average over all the torsional oscillations. So really the fast manifold, the fast solutions are largely irrelevant, but if you average over them, you get what you would have got if you were to ignore inertia altogether. So what we would say is that the ingredients are in place, just as Paul has said. We're making some progress here. We've got a stable scheme honoring the Taylor's constraint at every time step to machine precision. We've got these exact integrations in both geometries to spectral accuracy. We have a cheap method, which I haven't told you about, for finding the unknown flow UG. We automatically filter out this fast manifold, which we claim is not necessary, and the time step limitations are very much ameliorated, so you can take larger time steps. And again, like Paul, I would say 3D awaits. So we're just trying to put the ingredients in place. The rewards of filtering waves are the following. The time step is now controlled only by the CFL condition, and you have no waves, no alpha, no inertial waves to resolve. So, for example, if you're interested in reversals, or if you're interested in showing a dynamo working over decay times, if you really were to work at the parameter appropriate to the Earth, Rossby number of 10 to the minus 9, you would need to take something like 10 to the 10 time steps to see if it's self-exciting. No one does that. You can see the reason why. But I can't tell you exactly what the decrease in the number of time steps is going to be, but it's something certainly more than 1,000 times better than this condition. So it actually means that with this kind of approach, you're able to start working on really long time scales with geophysical parameters. So there's the conclusions. Taylor's inviscid ideas can be revived, as Paul has indeed shown. The Lorentz force is active at 0th order. We have a technical solution, stable time integration. We can deal with dynamics on timescales of, let's say, an order of 100 years plus with no viscosity. We've shown you the sort of relationship between the slow and the fast manifold, and what lies ahead is entirely uncharted territory. Thank you.
We have time for a quick question for Andy. Okay. Yes, Dominique? Can you repeat the question?
Yeah, what's the advantage of not using Taylor's differential equation? Taylor's differential equation tells you how to instantaneously have a Taylor state, but what you actually want to do is you want to advance forward in time, and you want to land in a Taylor state. And Taylor's differential equation does not tell you how to land in a Taylor state. You can be fortunate, for example, if everything is steady, for example, then the instantaneous problem is the same as landing in the Taylor state. But in general, it's not going to tell you how to take a finite length time step and land in a Taylor state.
Okay, thank you, Andy.